This is the second part of data hiding. It is intended for use in the course CGS 5131 at the University of Central Florida. My name is Rick Lineker. So we're going to talk about disk slack space now. And in general, this is unallocated disk space. This is normally referred to as slack space. But we need a little bit of clarification because there are really two different types of slack space. There's disk slack and file slack. We're going to first take a look at disk slack, and then eventually we'll get to file slack. The tool we're going to use for our exploration of disk slack is going to be WinHex. WinHex automatically shows you all unallocated space in a section or a group. So this is really convenient. You could actually hide all of your data into this unused or unallocated space, and you'd have to use a tool such as WinHex or some other disk editor, or maybe FTK or something like that to find it. The only problem with this is the data hidden in disk slack is susceptible to being overwritten. For instance, I could hide a bunch of information, and then someone might actually override all that by saving files to that disk. I've got a flash drive plugged into my computer, and you can see it has several files, 5 files, 1 subdirectory, and within the subdirectory it's got a single file. But this is actually not very much data. Mostly the USB stick is largely empty, which means there's a lot of unallocated space. So if there was a lot of unallocated space, then there'd be a lot of room to hide data. Okay, we're going to come back to here after we've hidden some data there. Okay, WinHex, let me go ahead and open up that disk. Okay, so the typical WinHex display. I've got my boot sector. I've got both FATs. Okay, and as you can see, initially, early on in the FATs, because there are several files, you have entries, but it's not long before you get to zeroed out entries. These are all zeroed out, so you can see I've got a lot of room left in that FAT section. So as you can see, there's a lot of space according to the FATs available. Here are the files. You can take a look at the binary representation. Here's the root directory, and there aren't many files listed in the root directory. Okay, but what we're interested in is the free space. Notice here that in the free space it said 7.6 gigs. It's almost the entire disk is free space. Here it's all zeroed out. Okay, so in the free space I could use any of this. So let's go ahead and go in here into the ASCII editor, and I'm going to say my name is Rick Lineker. Okay, then I'm going to go to the end of the free space and do the same thing. Okay, so now I've got it twice, and let me go ahead and save this. And just to make sure there's nothing up my sleeve, I'm going to go ahead and close everything out and rerun WinHex. But first, let's go ahead and refresh our directory here. We can't tell that anything was written to that disk looking at a file directory. Okay, let's rerun WinHex. Okay, open up the disk. Take a new snapshot because we did write to the disk. So now let's go ahead and search for Lineker and see what it finds. And this will probably take about 6 or 7 minutes. For my previous test, that's about what it took. So I'm going to snip part of this out of the video so you don't have to sit here and watch the green bar moving. Okay, so here you can see that it found Lineker 2 times, which is really what we would have expected. So let's go ahead and get rid of WinHex for right now. Okay, so now I'm in a directory where I have some test files. One of them is an audio file. It's really big. So let's go ahead and copy audio.mp3 to J. And that's a 40 meg file, approximately 41 actually. Okay, it's out there. And if we go to our display folder, we see audio. Let me move this down a bit. Audio.mp3. Okay. So let's rerun WinHex. And open that disk. Okay. And the reason we take a new snapshot is because we changed the disk by copying the audio file out there. Okay, so now let's go ahead and look for Lineker. And we'll search the disk for Lineker. And here again, this is going to take about 6 or 7 minutes, so I'll snip out part of this in the video. Okay, so it was only found one time, which makes sense because we copied a very large audio file onto the disk. And what that means is we overwrote the very first part of the free space. So if we click here where it found it, we can see that is actually at the very end of the free space. Now, if from back here we go to free space, you notice the first part of the free space doesn't say my name is Rick Lineker like it did before. That's because we took the free space, we wrote the audio file, and now the free space is all zeros as it was before. So it's actually now 40 megs into the free space. So now it's 40 megs into what was the free space. So that's that. And let's go ahead and open that up. Okay, so here I am in WinHex, and let's go ahead and open up an NTFS disk. We drive O, NTFS demo. Okay, so essentially you see something similar, except for remember we've got all these meta files. Okay, so I'm going to go into free space, which is 7.5 gigs. And the same thing is true here. My name is Rick Lineker. And as we saw, if you really want to be a lot safer, you go to the end and maybe type it there, somewhere there. My name is Rick Lineker. So that's about it for, I think I misspelled my own name. That's really bad. Okay, so if I saved it, it would get written to disk. I'm not going to save this, so I can save this example and keep the USB stick clean. Now, in just a minute, we're going to take a look at a program that can help you to write to in just a minute, we're going to take a look at a program that will allow you to write to a FAT32 USB stick. Okay, so I'm going to take my ubiquitous complete FAT analyzer program and rework it just a bit so we can write data into the unused space. So here I'm getting the FAT lists. Now what I do is I make sure I know where the root sector is. I create a little message buffer here. Copy in my name is Sam Smith. Now I set the file pointer. There's nothing magic about this 25,000. I used the calculator to figure out what would get me well past all the data, including that big audio data file. and then I just call write file. So let's go ahead and set a breakpoint here. Let's go ahead and run that until we get there. Okay. And I'm going to have to move Visual Studio over just a bit. Okay, so there's my message. Okay. I'm setting the file pointer, I'm writing the file, close the file, and I'm done. Okay. And we'll go ahead and open that disk. Okay. We'll go ahead and search for Sam Smith. Here again, this will take a while. Okay, so here we have the results. My name is Sam Smith, written actually quite a ways into the free space. So this is an example of how you can actually write your own program that writes into the free space. And I would actually be interested in having one or more of you develop an actual program with a front end that does this. That would be actually really nice. So let me know if you're interested, and I can waive one of your assignments, or I can give you extra credit, your choice. Now let's talk about file slack. I know we spent a few minutes talking about disk slack. File slack in my mind is a bit more useful than disk slack. The reason for this is a couple. So when I write a big audio file to the disk, it will never overwrite file slack. The second thing is, if you're really careful about file slack, it's very hard to detect. And right now we're only going to be doing the basic file slack, but our next presentation in part 3 of this, we're going to be talking about steganography and then how to apply steganography to file slack. So I think file slack is a much more useful approach to hiding data. So let's talk about it. So when you save a file, say in Notepad or anything else, the data is passed off to the file system for the target storage device. And most of the time that's going to be a hard drive or a USB stick or something like that. So all storage media, whether it's a hard drive or an SSD, flash drive, CDs, DVDs, they're broken up into sectors. And I know we've already talked about this a number of times. The sector usually contains 512 bytes, as we've said. Not always, but usually. And that's just about the right size for the first paragraph of the Declaration of Independence. The reason I bring this up is because we're going to be using the Declaration of Independence actually for an example. But since modern storage devices have huge numbers of sectors, we need to somehow simplify their management of these sectors. So they group the sectors into larger units called clusters, which, as we've already specified, that most of the time a cluster has 8 sectors. Now, if it's got 8 sectors, they're always contiguous, or always one after the other. You can have clusters all over the hard drive, but within a cluster you always have 8 contiguous sectors. This gives a total of 4,096 bytes. Now, here again, remember that some formatting options can change the sector size and the number of sectors in a cluster. But 99.999% of the time, it's going to be 8 sectors in a cluster, 512 bytes in a sector, for a total of 4,096 bytes in a cluster. So this is a cluster layout. I've got a single sector shown here, 512 bytes, and just as an illustrative, I've got when in the course of human events. So you know that could fit the first paragraph of the Declaration of Independence. So we've got a cluster here pictured. The cluster has 8 sectors for a total of 4,096 bytes. Note that the sectors have to be contiguous. But this leads to what could be a lot of wasted space. An interesting byproduct of this organization of sectors and clusters and bytes is that most files which are written to disk have leftover space after the actual file data. That's because all files are going to be written, file size is always written to disk in multiples of 4096. Now, just to let you know, that is a partial inaccuracy. NTFS has what are called resident files, and I'm not going to cover those right now. Very small files in NTFS actually have no clusters. The actual data can be stored in the MFT. But I'm sort of glossing over that right now and talking about files that are, say, greater than or equal to about 1K. I did a lot of experimentation several years ago, and I think for my experiments it was 268 bytes or less would be stored as a resident file. But let's say you want to save a file with 1024 bytes of data. That's only 2 sectors. 512 bytes per sector times 2 is 1024. So now you've got this entire cluster allocated on disk, but you've only actually written 2 sectors. So now you've got a ton of leftover space at the end. So since the smallest unit of space the file system uses is a cluster, it will always write a minimum of 8 sectors or 4096 bytes. Of course, unless it's a resident file, which we've already talked about. So your 1024 byte file actually occupies 4096 bytes on the disk. The unused space is 3072 bytes. Lots of space for black hats, or even enterprising white hats to hide stuff. Ignoring the amount of space that the cluster occupies, the file size that the operating system will report is only that of the actual file data, which in this case is 1024. Nobody will notice that there's data written into the slack space. Okay, so here's how this wasted space layout happens. The red is the actual file data, the blue is the unused disk space past the actual file data. So here we've got a single cluster once again, and the first 2 sectors are occupied with file data. After that, you've got 3072 bytes which are unused and completely ready to have data hidden in them. From a developer's point of view, slack space is normally inaccessible. I know if you do any kind of C programming, you have fopen, fwrite, fread, fclose, and so forth. None of those say write to the slack space. It's just not part of the normal API. So in order to read from and write to slack space, you must actually rely on some more obscure and poorly documented system APIs. I'm not really sure if they're poorly documented as such, but there just aren't that many references online or in books, so it's just harder to find. For this reason, slack space is off limits to the majority of programmers. In addition, your program needs to operate in administrative mode too. A lot of people forget this. So now, enter the black cat who wants a safe place in which to hide data. Let's say, for instance, that he wants to hide a list of credit card numbers, or a list of passwords, or a list of really anything. He can write special software to access the slack space by relying on the system APIs. Okay. So, like I said, it's not impossible. It can be done. In fact, it's done all the time. Then he can write the list of credit card numbers into the slack space of a seemingly normal file. Of course, this takes some effort and a fairly capable programmer, but it can be done and is done on a regular basis. Okay. Detection. Well, this is difficult. It is rarely done. So almost never will anybody detect data that was written in the slack space. And we're actually going to follow up on this in part 3 of this series and talk about ways to really make it hard to detect. The only tools that you may be able to use to extract slack data are like forensics tools such as FTK. You can actually use WinHex to do it. And examiners must implicitly instruct their software to address the slack space, since the default settings don't usually add slack space to their list of investigative techniques. So how do you write to the file slack? Methodical, white hat point of view, where thorough examination of digital systems is used to reveal evidence. There's a great value in taking the black hat point of view. From the black hat perspective, my students get a more comprehensive understanding of the science of digital forensics. I have a Slack utility that I have been developing over the years. Some students have helped me, and I actually welcome your help. If you're interested, please let me know. And we're actually going to take a look at that utility in just a couple of minutes. Okay, so here is a Visual C++ program that I wrote in Visual Studio 2013. And it's an MFC dialogue application. MFC stands for Microsoft Foundation Classes. So it's a dialogue-based application, just to kind of keep it small and simple. So let's go ahead and run it. It does have a GUI, which is good because then we can go ahead and select these files without having a really ugly command line parameter. My name is Arnold Palmer, and that's in reference to him. He just died, so we're trying to honor him. Click here, store the message. So now let's go ahead and step through this. This mounted drive, just as we do a 2-upper, so it's really easier. And we have these two statics up here. And keeping these, just setting these, just makes it a lot easier than doing a couple of sprintfs. Okay. So the reason we need to get the file system format is because NTFS and FAT32 are different. NTFS, the clusters that are reported, or the cluster map that's reported, is direct. You can count on that and do a seek on the disk. However, in FAT32, they're actually logical. So you actually have to add an offset into the data. So let's see what we have here. We have FAT32. Okay, so that's going to be a big clue. Okay, so let's keep going. Now you've seen this before, get disk free space, so we can get sectors per cluster and bytes per sector. Very important, just in case this particular device is not standard. Okay, we create the file for reading. Now we're going to get the file size. And here we're just making some pretty simple calculations. We want to get the number of clusters, the bytes per cluster, the number of clusters, and the number of sectors. And this is going to help us this will help us find the place on the disk where the file resides. Okay, this next part is we need to find the file extents. Okay, and within each file extent then is one or more clusters. Okay, so we make this Windows API call. Here again, this is what I was referring to. Finding documentation on this is relatively difficult. So that's why earlier in this presentation I mentioned that it's poorly documented. It's not really poorly documented, it's just hard to find. So I go ahead and get this. Close the handle because I'm done with that. Just want to make sure everything passed. Okay, now what I do is I create a buffer for my cluster map. And I walk through the extents, and here there's only going to be one. Okay, remember, an extent is anywhere from 1 to 1.5 million clusters. Okay. I get the number of clusters in this particular extent. Now, remember, I can have more than one extent. Okay, I loop through, and I put the cluster number into that buffer. Now this is a really small file. The file actually is less than a single cluster. So that's why it's just got a single cluster and a single extent. Now here's something that took me a long time to figure out. that you really need to go ahead and offset if you're using FAT. So here I'm making a check to see if my file format is FAT, and it is. So now I actually have to go in and read the boot sector. Okay, we've already talked about the boot sector a bit. And the BIOS parameter block and the extended BIOS parameter block are of special interest to us here. Okay, so we're going to get the reserve sector count from the BIOS parameter block to use, and we're going to use the logical sectors per FAT. And that way we know what to skip. We're going to skip all the reserved. We're going to skip the 2 FATs. Okay, so reserved plus the FATs. So this lets us calculate what to skip. So we seek, and for whatever reason, I have some old legacy code here where I'm reading some directory entries. You can actually ignore this. I need to take this out. Like I said, this is a program under development, and so these 2 lines here have no place in what I'm doing at this moment. Close the handle. Okay, so now I can go ahead and do my calculations so I know where to offset to. Okay, now I go through the cluster map, and I add clusters, add to extend. That's 4096. Okay, now I'm going to open the drive for writing. So I open the drive with a valid handle there. If the handle isn't valid, we'll drop out. Now I have to use a large integer. Now I have to use large integers because these values get very large very fast, and it will surpass the ability of a D word to contain them. Okay, so here's the cluster number. Notice this puts me in the very last cluster in this list. It might be, since it's 1, this is going to equate to 0, but it might be 100 or something. Okay, I'm going to go ahead and calculate my number of bytes per cluster. And finally, seek2 equals the cluster number times the bytes per cluster. Okay, so now we're going to add however many sectors the file actually took. So the file actually took 4 sectors. And so since we have this whole cluster, we need to seek 4 sectors in order to make sure we avoid the data that's already there, or we'll be hosing up our regular data. We add. We seek to where we're going. Message buffer. My name is Arnold Palmer. Message length 24. We write the data. We close the file, and we are done. And our UI comes back up, and we're good to go. Okay, let me go ahead and bail out of that. Minimize this. Let's get our old friend WinHex. Open disk. Getting your snapshot. And we should actually Arnold. Just search for Arnold. And when it shows that it's found 1, I'll go ahead and stop the search. Okay, so it shows 1 hit. That's I happen to know, since I know this disk, that's all. So I'm going to go ahead and abort this search. Arnold was found 1 time. Here we go. And notice if we scroll up, we see the end of that's sector 4 of the Declaration of Independence. So there we wrote that to disk. We wrote that to the SLAC file. And I can write large files to this USB stick all day long, and it won't overwrite this SLAC space. Here again, as with that thing we did in part 1, I'm looking for help so that I can turn this into a peer-reviewed academic article. While SLAC space isn't incredibly new, the approach I'm taking with this and the approach I'm going to be taking in part 3 are actually fairly unique. So this is what I need help with: the following: code testing and cleanup and commenting. Need to look for also other similar existing techniques. And I know they're out there. For instance, I know Metasploit has something called Slacker. and it's largely targeted towards a Linux base. I need someone to make the usual charts and graphs to kind of break up the text so the article is more appealing and more interesting. Need someone to kind of research the journal part of it and to help with the submission part of it. Obviously, we need technical and grammar editing and maybe other things that I haven't thought of. So if you're interested, send me an email to my UCF address if you're interested. Also send me what times you're available to maybe meet or get together or do a Skype or a Google Hangout or something. And your name will get added to the article byline if you help.